the same cyclic subgroup. But let's look at some other examples. Well, let's look at the groups of order 4. Remember that up to isomorphism there are two groups of order 4. There's the integers modulo 4 under addition, and there's also the Klein group So do we need to do the group tables? Well, we've done this once or twice now. Usually we would call the integers modulo 4 0, 1, 2 and 3. And just to remind you that 1 isn't really the integer 1, it's actually the equivalence class 1, 5, 9 going off in both directions. It's all the integers that leave remainder 1 on division by 4. But the group table for addition looks like this. So that's addition modulo 4, that's a group of order 4. And then there's the Klein group. Well, we could use the same symbols, 0, 1, 2 and 3. But I'll probably use different notation just to keep things clear. Identity element and then 3 non-identity elements A, B and C. If you want, you can think of V as the direct product of Z2 with Z2 as we did last week, in which case E would be 0, 0. A would be, say, 1, 0. B would be 0, 1. And C would be 1, 1. So we did actually discuss direct products last week, and in fact our kind of only example of a direct product that we've worked with so far was the Klein group. So we take the simplest non-trivial group, which is integers modulo 2 under addition, and we take the product of that with itself. And we get the following table. Well, E is the identity element. And the way you recognize the Klein group, remember, is that every element is idempotent. Its square is the identity. Sorry, I shouldn't have used the word idempotent there. Its square is the identity. Okay, so there's a line of identities down the principal diagonal. And then we fill this in the only way that we can to make it a group. So I think it looks like that. So that's the group table for the Klein group. And these are not isomorphic. You can see that because of this line of diagonals, line of the identities down the diagonal, that Z4 doesn't have that. So these are not isomorphic. And as we've mentioned before, any group of order 4 is isomorphic to one or the other of these. These are the only two groups of order 4. And they've got different properties about cyclic subgroups. So we're going to now think about cyclic subgroups of these. And we'll see, in fact, that Z4 is itself a cyclic subgroup of itself. We say that Z4 is cyclic. It's actually generated by one of its elements. So let's see that. So now let's look at Z4. Well, we can take any element we like and look at the subgroup generated by it. Now we've just got to have a word of warning here. We're using additive notation for Z4 because that's natural. We're doing addition modulo 4. So if I've got A in Z4, I'm going to be talking about things like A plus A rather than A times A. So whereas I would write A times A as A squared using multiplicative notation, I would write A plus A as 2A. So when we're using additive notation, a squared becomes 2a quite naturally. Okay? So we've been using multiplicative notation in general, and of course also when we've got multiplication of numbers or matrices, but when we're doing addition modulo 4, we really should be using additive notation. So a plus a is 2a. Okay? That's just a word of warning. So let's consider, say, 0 in Z4. That's the identity element. Then what's the group generated by 0? Well, what can I do? I can look at 0, then that's, if you like, 1 times 0. I can look at 2 times 0, but I'm always going to get 0. And I can look at negative powers, if you like, of 0, but the only thing I'm going to get is 0, and that's always the case. The subgroup generated by the identity element is just a trivial subgroup. So that's certainly a subgroup of Z4. It's not a very exciting one. What about taking 1 in Z4? Now remember, 1 is not an identity element or anything for addition. It's just an element of Z4, one of the 3 other elements other than the identity. So we're going to look at, if we were doing multiplicative notation, we'd be looking at 1 to the power 1, 1 to the power 0, 1 to the minus 1, 1 squared, 1 cubed, and so on. But now we're using additive notation, so we're going to be looking at minus 1 times 1, 0 times 1, 1 times 1, 2 times 1, 3 times 1, and so on. So that's the analogue of that, using additive notation. So that's 1, that's 0, that's minus 1, which is the inverse of 1 in Z4, which is actually 3. This is 2, this is 3. 4 times 1 is 3 plus 1, which is 0. So notice that the powers of 1 give us the whole group. So as soon as we look at the number 1, the subgroup generated by 1 is actually the whole group. That's fine. Certainly Z4 is a subgroup of itself. And if you get the whole group by looking at the subgroup generated by a particular element, we say that the whole group is cyclic. So Z4 is an example of a cyclic group. So cyclic group means it's generated by one of its elements. Well, we can actually generate Z4 by another element as well. Let's take the element 3. And we could ask, what's the subgroup generated by 3? So again, we do, if we wanted to look at all the powers, we'd look at minus 2 times 3, minus 1 times 3, of course going off with all the negative powers, then 0 times 3, 1 times 3, 2 times 3, 3 times 3, and so on. We can compute all these. So of course we start with 3, and then we do, if we're going in this direction, we do 3 plus 3, which is 2, and then we do 3 added to that, which is 1, and so on. This is always the identity, remember. That's the analogue of 3 to the 0, but we're using additive notation. So in multiplicative notation, we'd have the identity element, which is 0. Minus 1 times 3 is minus 3, which is the additive inverse of 3, which in fact is 1. because 1 plus 3 is 0. And then that's minus 2 and so on. So again, by looking at powers of 3, in other words, adding 3 repeatedly to itself, because we're now doing additive notation, so we're adding 3 repeatedly to itself rather than multiplying repeatedly, we actually get that we get all the elements 0, 1, 2, 3 of Z4. So in fact, the subgroup generated by 3 is the same as the subgroup generated by 1, and in fact they're equal to the whole group. So this is an example of where the same one cyclic group can have 2 different generators. So the generator is not unique, because both 1 and 3 generate Z4. The subgroups we've got so far, in a way, are not, they are interesting in one way, but in another way they're not, because we've got the trivial subgroup and then we've got the whole thing at the other end. But there's an element of Z4 that we haven't looked at yet, which is 2. Well, let's do this a bit more quickly. What can I get by adding 2 to itself repeatedly? Well, I can get 2, but then if I do 2 plus 2, I get 0. And those are the only 2 things I can get. So by adding 2 together repeatedly, the only things I can get are 0 and 2. So we get actually now a slightly more interesting subgroup of Z. In other words, something which is neither trivial nor the whole thing. So this is a cyclic subgroup of Z4 generated by 2. And in fact, that 2 is the generator here. Well, I'll play this game with other integers modulo, and you'll find that Z sub n in general, not just n equals 4, Z sub n in general is a cyclic group, and you can think about how many generators it's got. And we'll go on to talk about some of those things next week. Before we finish today, in the last 3 minutes, let's look at the other group of order 4. Well, so remember we were writing this as having elements, the identity element and then 3 other elements. Well, the subgroup generated by the identity, and we're now using multiplicative notation again, by multiplying the identity by itself repeatedly, the only thing you can get is the identity. What about A? Well, remember, A squared is the identity. So if I start with A, and then I multiply it by itself, A squared is the identity, so A cubed must be back to A, and so on. A to the 0, A to the 0, of course, is the identity. A to the minus 1 must be A, because A times A is the identity, so A inverse is itself. So in fact, the only things we generate are E and A. So that's a subgroup of order 2 sitting inside the Klein group. And similarly, because there's a symmetry between A, B and C, we get a subgroup of order 2 from B and a subgroup of order 2 from C. So that's gone through all 4 elements of the Klein group. None of them generate the group itself. So this is an important point, that Z4, which is one of the groups of order 4, is cyclic. It's generated by something in the group, in fact by 2 different things. So Z4 is cyclic, but V is not cyclic because no matter which element of V I pick, I never generate the whole group. These are all proper subgroups. So Z4 is cyclic and the Klein group is not cyclic. So that's a group theoretic difference between the two groups of order 4. Okay? Well, we'll leave it there because unfortunately we've run out of time. Thank you for coming. Worksheet 5 has been on Blackboard for